Welcome! In this session, we'll explore an interesting problem titled Invalid Transactions. This problem challenges us to analyze a list of transactions and identify which ones are considered invalid based on specific criteria. It's a great opportunity to practice string manipulation, hashing techniques, and logical problem solving. Let's dive in. In this problem, you're given an array of strings called transactions, where each entry describes a transaction's details in a specific format: name, time, amount, and city. The name represents the person involved, time is the transaction's timestamp in minutes, amount is the monetary value of the transaction, and city specifies where it occurred. A transaction is considered invalid if its amount is greater than $1,000, or if there is another transaction by the same person in a different city within a 60-minute time window. Your task is to identify and return all such transactions that are invalid. The result can be returned in any order. To clarify the input and output formats, the input is an array of strings, where each string is formatted as name, time, amount, city. The output is a list of strings containing only the invalid transactions from the input. For example, if the input transactions are Alice 2800 MTV, Alice 5100 Beijing, the output would be Alice 5100 Beijing. This is because the second transaction occurs within 60 minutes of another transaction by the same person, and the two transactions are in different cities. Looking deeper into this example, the first transaction Alice 2800 MTV is valid. Its amount does not exceed $1,000. And there are no conflicting transactions within 60 minutes in a different city. However, the second transaction Alice 5100 Beijing is invalid because it occurs within 60 minutes of the first transaction and is in a different city. In another example, consider Alice 2800 MTV, Alice 1200 MTV. Here, the second transaction is invalid because its amount exceeds $1,000. While the first transaction remains valid since it satisfies all the conditions. Now, let's examine a third example. If the transactions are Bob 1200 MTV, Bob 2100 Beijing, the output would be Bob 1200 MTV. The first transaction is invalid because its amount is greater than $1,000. The second transaction, however, is valid because its amount is under $1,000. And there are no time conflicts with other transactions in different cities. Additionally, the constraints for this problem specify that the input array can have up to 1,000 transactions, and each transaction string is always formatted correctly with name, time, amount, and city. Finally, the constraints further clarify the problem's boundaries. The amount value will always be between 0 and 2,000, and the time value will always be between 0 and 1,000. Edge cases to consider include scenarios where all transactions are valid, or all are invalid. For instance, all transactions might exceed $1,000, or several may violate the 60-minute rule. You should also handle cases with multiple transactions occurring at the exact same timestamp, whether in the same or different cities. Additionally, ensure your solution is efficient enough to handle the upper limit of 1,000 transactions smoothly. To solve the problem of identifying invalid transactions, we first need to understand the conditions that make a transaction invalid. A transaction is considered invalid if its amount exceeds $1,000. Additionally, a transaction is invalid if there exists another transaction with the same name, where the time difference between the two transactions is at most 60 minutes, but the cities are different. Our task is to identify all such invalid transactions from the given input array. To achieve this, we need to carefully analyze the transactions and find an efficient way to check these conditions. Let's explore some possible approaches to tackle this problem. One possible way to solve this problem is the brute force approach, which involves directly comparing each transaction with every other transaction. The idea is straightforward. First, parse each transaction into its components: name, time, amount, and city. Then, for every transaction, compare it with all others to check if the amount exceeds $1,000 or if another transaction with the same name exists that meets the invalid conditions of time difference and city mismatch. While this approach ensures correctness, it is highly inefficient for large inputs since the time complexity is n squared, where n is the number of transactions. This inefficiency arises from repeatedly comparing the same transactions, which leads to redundant computations. Additionally, the space complexity is n, as we need to store the invalid transactions. Due to these drawbacks, this method is not practical for large datasets. To address the inefficiencies of the brute force approach, we can optimize the solution by grouping transactions by their name. Since the invalidation criteria depend on transactions with the same name, this grouping reduces unnecessary comparisons. After parsing the transactions, we organize them into groups based on their name. Within each group, we evaluate whether any transaction has an amount exceeding $1,000 and whether any pair of transactions within the group satisfies the invalid conditions, such as a time difference of 60 minutes or less in different cities. This method significantly reduces the number of comparisons needed, as we only focus on transactions within the same group. The time complexity is O, n*m, where n is the number of unique names and m is the average number of transactions per name. The space complexity remains O, n, for storing the groups. This approach is more scalable and avoids the redundancy of the brute force method. Another approach to solving this problem is to sort the transactions by time, which allows us to use a sliding window technique to check the invalidation conditions. After parsing the transactions, we sort them first by name and then by time. For each transaction, we only need to check other transactions within the next 60 minutes for differences in city, reducing the number of comparisons. While sorting introduces an O, n log n, overhead, the comparisons within the sliding window only take O, n, resulting in an overall time complexity of O, n log n. The space complexity remains O, n. However, sorting-based approaches may be less efficient for smaller datasets, as the overhead of sorting might outweigh the benefits of reduced comparisons. This method is more structured but can be less intuitive to implement compared to grouping by name. The optimized approach of grouping transactions by name is the most balanced and practical solution for this problem. It strikes a good balance between time and space efficiency while avoiding the redundancy of the brute force method. By focusing only on smaller groups of transactions per name, we can minimize unnecessary checks, making it easier to implement and debug. While this approach may require additional memory for grouping, it is well suited for average cases and scales effectively with larger datasets. Sorting-based methods, though viable, are less intuitive for this particular problem and can introduce sorting overhead. The key takeaway is that the problem revolves around grouping transactions by name to streamline the validation process. This chosen strategy is robust, scalable, and aligns well with the problem's constraints and requirements. To solve the problem of identifying invalid transactions, we need to evaluate each transaction against two criteria. The first is whether the transaction amount exceeds $1,000, and the second is whether it conflicts with another transaction. A conflict occurs when two transactions share the same name, happen within 60 minutes of each other, and occur in different cities. The initial step in our algorithm is to parse the input transactions. Each transaction is provided as a string in the format name, time, amount, city. Our goal here is to convert these strings into a structured format, such as dictionaries or tuples, for easier processing. For example, a transaction like Alice 2800 New York would be parsed into a dictionary with keys like name, time, amount, and city. This parsing process involves splitting the string by commas and converting fields like time and amount into integers for numerical operations. Once parsed, we move on to the next step, identifying transactions where the amount exceeds $1,000. By iterating over the parsed transactions, we check if the amount field is greater than 1,000. If it is, we mark the transaction as invalid, typically by adding its index to a set called invalid_indices. This set will help us track all invalid transactions efficiently as we proceed to the next steps. To streamline the process of finding conflicting transactions, we group all transactions by the name of the person involved. This is done using a dictionary where the keys are the names and the values are lists of transactions associated with that name. For instance, all of Alice's transactions are grouped together, making it easier to focus only on relevant comparisons. This grouping approach reduces the need for redundant comparisons across unrelated transactions. Once grouped, we then check for conflicts within each group. The transactions are sorted by time to simplify the comparison process. Sorting ensures that transactions close in time are positioned next to each other, and this helps us efficiently identify conflicts. For each pair of transactions within the same group, we check two conditions. First, the absolute difference in their times must be 60 minutes or less. Second, the transactions must occur in different cities. If both conditions are met, both transactions are marked as invalid by adding their indices to our invalid_indices set. Using a nested loop or a sliding window approach allows us to perform these checks efficiently, minimizing the computational cost. After identifying all invalid transactions, the next step is to compile the results. We convert the indices stored in the invalid_indices set back into their original transaction formats. This ensures that the final output reflects the exact transactions that were flagged as invalid. The algorithm then returns this list of invalid transactions as the result. There are several key insights that make this approach efficient. Sorting transactions by time within each group ensures that we only need to compare nearby transactions, reducing the overall complexity of the algorithm. Using a set to store invalid indices is another optimization, as it prevents duplicates and allows for constant time lookups. Grouping transactions by name further enhances efficiency by narrowing down the scope of comparisons to only those transactions that are relevant to each other. In terms of data structures, dictionaries are used for grouping transactions by name, with each key corresponding to a person and each value being a list of their transactions. The invalid_indices set ensures uniqueness in fast lookups, while parsed transactions are stored in a list for structured access to fields like name, time, amount, and city. The use of specific data structures enhances the algorithm's readability and performance. For instance, the dictionary used for grouping transactions allows us to quickly access all transactions associated with a specific name, avoiding unnecessary comparisons across unrelated names. The set for invalid indices ensures that we don't accidentally mark the same transaction multiple times, while also enabling O1 lookups for quick checks. Similarly, storing parsed transactions as dictionaries or tuples simplifies the process of accessing individual fields like time or city. Now, let's consider the operations involved in this algorithm. Parsing the input strings into structured formats is the first operation, which involves splitting the strings and converting fields to appropriate data types. This has a linear complexity of O(n), where n is the total number of transactions. Grouping the transactions by name is the next operation, which also involves iterating over all transactions and inserting them into a dictionary. This step is also O(n) in complexity, as we only make a single pass through the data. Sorting transactions by time within each group is a key operation that simplifies the process of conflict detection. For each group, the transactions are sorted based on their time field. The complexity of sorting depends on the number of transactions in each group, but overall, sorting across all groups adds a complexity of O(n) log n. Once sorted, we move on to the conflict detection step. This involves comparing transactions within each group to identify potential conflicts. Using a sliding window or nested loop, we check whether two transactions are within 60 minutes of each other and occur in different cities. The complexity of this step depends on the number of comparisons required within each group, which we'll denote as K. The total complexity for conflict detection is approximately O(k) per group. Combining these steps, the overall complexity of the algorithm is dominated by the sorting and processing steps, resulting in an approximate complexity of O(n) log n. Finally, it's important to consider edge cases and ensure the algorithm handles them correctly. For example, if there are no transactions provided, the algorithm should simply return an empty list. If all transactions are valid, the algorithm must ensure that no transactions are mistakenly flagged as invalid. Additionally, we must account for scenarios where a single transaction violates both criteria. For instance, a transaction might have an amount exceeding $1,000 and simultaneously conflict with another transaction in terms of time and city. In such cases, the algorithm should handle both violations properly and mark the transaction as invalid. For large inputs, such as datasets with up to 10,000 transactions, the algorithm needs to maintain efficiency. The grouping and sorting operations are designed to scale well with larger inputs, ensuring that performance remains acceptable even as the number of transactions increases. By addressing these edge cases and scaling considerations, the algorithm becomes robust and reliable for a wide range of scenarios. The code solves the invalid transactions problem by identifying transactions that meet specific invalid criteria. It begins by parsing the input transactions, breaking each transaction string into meaningful components: name, time, amount, city, and the original transaction string. These parsed details are stored in a list for later processing. The solution uses a nested loop to compare each transaction against others. The outer loop iterates through each transaction, and the inner loop checks for conflicts with all other transactions. Two conditions are checked: 1, if the transaction amount exceeds $1,000, or 2, if there exists another transaction with the same name, occurring within 60 minutes, but in a different city. If either condition is met, the transaction is marked as invalid by adding it to a set. The use of a set ensures that duplicate invalid transactions are automatically removed. Finally, the set is converted to a list and returned as the output. This ensures the output contains all unique invalid transactions in any order. This implementation carefully handles edge cases, such as multiple transactions with the same name and conflicting times, by using a nested loop to exhaustively compare each transaction with all others. It also ensures efficiency by storing transactions in structured tuples, allowing quick comparisons of relevant fields like name, time, and city. The algorithm has a time complexity of O(n) squared, due to the nested loop, which is reasonable given the constraints of the problem. Here, we begin by importing the necessary Java utilities and defining our solution class. The key method, invalid transactions, takes an array of transaction strings as input. Each transaction is structured as name, time, amount, city. To make processing easier, we first parse these strings into a structured format. For this, we split each transaction string by commas to extract the name, time, amount, and city. These values are then used to create instances of a helper class, transaction, which stores the parsed data along with the original string. These parsed transactions are added to a list for further analysis. Next, we define a hash set, invalid transactions, to store transactions that meet the invalid conditions while ensuring no duplicates. The first condition we check is whether the amount of any transaction exceeds 1,000. If this is the case, we immediately add the original transaction string to the invalid set. The second condition involves comparing transactions to identify those that occur in different cities for the same name within a 60-minute window. This is where we set up the framework to iterate through all possible pairs of transactions for further validation. Now, we implement the logic to handle the second invalid transaction condition. Using a nested loop, we compare each transaction, T1, with every other transaction, T2, in our parsed transactions list. To avoid self-comparison, we skip the iteration when the indices of T1 and T2 are identical. For the condition to be satisfied, both transactions must belong to the same person, indicated by matching names. Additionally, the transactions must occur in different cities, and the absolute difference in their times must be 60 minutes or less. If all these criteria are met, both transactions are deemed invalid. We add their original strings to our invalid transactions set. The use of a hash set here ensures that duplicate entries are automatically filtered out. Once all pairs of transactions have been processed, we proceed to convert the set of invalid transactions into a list, which is the required output format. This ensures the result is returned in a form that matches the problem's expectations. The final part of the implementation focuses on the helper class, transaction. This class is designed to encapsulate the details of a transaction in a structured way, making it easier to compare and process the data. It includes fields for the name, time, amount, city, and the original string representation of the transaction. The constructor of the transaction class initializes these fields using the input values provided during object creation. This design makes the transaction class a self-contained unit for transaction data, simplifying the logic in the main invalid transactions method. By organizing the data this way, we ensure clarity and maintainability in the code, as each object represents a single transaction with all relevant details accessible. Here, we begin with a simple example to demonstrate how invalid transactions are identified. The input consists of two transactions for Alice. First, we parse each transaction, extracting the name, time, amount, and city fields while keeping the original transaction string for reference. This gives us a structured list of parsed transactions. Next, we initialize an empty set called invalid to track any transactions deemed invalid. For the first transaction, Alice, 2800 MTV, we check if the transaction amount exceeds 1,000. Since 800 is within the limit, the transaction is valid based on the amount. However, we then compare this transaction with the second one, Alice 50 1200 Beijing. Since the names match, the cities differ, and the time difference is within 60 minutes, both transactions are marked as invalid. These transactions are added to the invalid set, which will eventually form our output. Now that both transactions have been checked, we move to the second transaction, Alice 50 1200 Beijing. However, since this transaction was already marked as invalid during the comparison with the first transaction, no further checks are needed. At the end of the process, the invalid set contains both transactions, Alice 2800 MTV and Alice 50 1200 Beijing. These are returned as the final output for this example. In the next example, we consider a case with multiple names but no invalid transactions. Here, the input includes transactions for Bob and Tom. As usual, we start by parsing the transactions into a structured format. After that, an empty invalid set is initialized to track any invalid transactions. For the first transaction, Bob 10,500 New York, the amount is within the limit, so we proceed to compare it with the other transactions. The first comparison is with Tom 15,700 SF. Since the names don't match, we skip this transaction. Next, we compare it with Bob 70,300 New Jersey. Although the names match, the time difference between the two transactions is greater than 60 minutes, which means they are valid when considered together. Moving to the second transaction, Tom 15,700 SF, we verify that the amount is within the limit. Since no other transactions have matching names, there are no further comparisons, and this transaction remains valid. Lastly, for Bob 7300 New Jersey, the amount is also within the limit, and no issues are found during comparisons. As a result, the invalid set remains empty, and the final output for this example is an empty list, indicating no invalid transactions were detected. Now, let's examine a scenario where a large transaction amount causes a violation. In this example, the input consists of two transactions, Bob 10,1500 New York and Alice 15,700 lot. After parsing, we obtain a structured list, and the invalid set is initialized as empty. For the first transaction, Bob 10,1500 New York, the transaction amount exceeds 1,000, which is a direct violation. Therefore, this transaction is marked as invalid and added to the invalid set. For the second transaction, Alice 15,700 blah, the amount is within the limit. Since no other transactions have the same name, there are no additional comparisons, and this transaction remains valid. At the end of this process, the invalid set contains only Bob 10,1500 New York, which is returned as the output. This example highlights how transactions with excessively large amounts are immediately flagged as invalid without requiring further comparisons. Here, we begin analyzing the time complexity of the solution to problem number 1169. The first step involves parsing the transactions. Each transaction string is split into its components, such as name, time, amount, and city. If there are n transactions and each string has an average length of k, the parsing step takes k time per transaction, resulting in n*k for all transactions. After parsing, the outer loop processes each transaction individually. For every transaction, a simple check is performed to see if the transaction amount exceeds 1,000. Since this check is a constant time operation, the contribution here is n for n transactions. These steps lay the foundation for understanding the overall time complexity of the algorithm. The time complexity analysis continues with the inner loop. For each transaction in the outer loop, the inner loop iterates through all transactions again, creating a nested structure. Within the inner loop, three key operations are performed: comparing names, checking the time difference, and comparing cities. Each of these operations takes constant time, 1. Since the inner loop runs n times for each of the n iterations of the outer loop, the nested loops contribute n squared to the overall complexity. When we combine this with the parsing step, which is n*k, the total time complexity becomes n squared plus n times k. However, for large inputs where n dominates, the n squared term becomes the most significant, making the worst-case time complexity n squared. Next, we evaluate the space complexity of the solution. The first major contributor to space usage is the parsed list, which stores the details of all transactions. Each transaction requires O, K, space, leading to a total of O, N asterisk K, for N transactions. Additionally, the invalid set stores references to transactions identified as invalid. In the worst-case scenario, where all transactions are deemed invalid, this set would require O, N, space. However, the dominant factor in space usage is the parsed list, which results in an overall space complexity of O, N asterisk K. This analysis highlights that the algorithm's space requirements primarily depend on the size and structure of the input data. Looking at the different scenarios for the algorithm, in the best case, all transactions are valid, meaning the inner loop does not add any entries to the invalid set. Even so, the algorithm must still compare all transaction pairs, keeping the time complexity at O, N squared. In the average case, some transactions are invalid, but the number of comparisons remains roughly the same, so the time complexity also stays O, N squared. In the worst case, all transactions are invalid, requiring every possible comparison, which results in the same O, N squared, time complexity. Now, if we compare this brute force approach with a potential optimization, a more efficient method might involve grouping transactions by name using a hash map. This could reduce the comparisons to transactions within the same group, potentially improving the time complexity to O, N asterisk G, where G is the average group size. This optimization minimizes redundant comparisons between unrelated transactions. In conclusion, the current solution has a time complexity of O, N squared, and a space complexity of O, N asterisk K. While the approach is straightforward and systematically handles all edge cases, it is not scalable for large datasets due to the quadratic time complexity. By leveraging pre-processing techniques, such as grouping transactions by name or using more efficient data structures, redundant comparisons can be avoided, leading to significant improvements in runtime. These optimizations are worth considering for scenarios involving high transaction volumes or strict performance requirements. One of the most common mistakes is assuming the input data will always be perfectly formatted. In real-world scenarios, and especially in interviews, inputs can include missing fields, invalid values, or malformed strings. This is why it's crucial to validate the format of transactions before you start processing them. Another frequent oversight is focusing only on individual transactions and ignoring how they relate to others. For instance, a transaction might only be invalid because it conflicts with another one in a different city within a 60-minute window, even if it looks fine on its own. Overlooking these cross-transaction rules can lead to incomplete solutions. Finally, using inefficient data structures, like nested loops, to check transactions against each other can quickly lead to performance issues when dealing with large datasets. Opting for optimized structures, such as hash maps, can make your solution much more efficient and scalable. Another critical area to watch out for is edge cases. These can include scenarios like multiple transactions happening at the exact same time, transactions with the same name but in different cities, or cases where a mix of valid and invalid transactions exists. Overlooking these edge cases can cause your solution to fail during testing. Additionally, you must ensure you're identifying and returning all invalid transactions, not just the first one you find. If your solution misses even one invalid transaction, it will likely be marked incomplete. It's essential to use thorough testing to catch these issues and ensure your solution is comprehensive. A key way to approach this problem is to break it into two parts. First, identify transactions with amounts greater than 1,000, since those are straightforward to flag. Then, focus on cross-checking transactions with the same name for potential conflicts, like timing or city mismatches. To optimize this process, use a hash map to group transactions by name. This reduces the time complexity of cross-checking from O, N squared, to O, N, making your solution much more efficient. Also, remember to consider scalability. As the input size grows, inefficient solutions can become impractical, so always think about how your approach performs with larger datasets. Lastly, communication is key during interviews. Clarify any requirements or assumptions with your interviewer, such as how to handle edge cases or what format the output should take. This problem is closely related to others that involve grouping data or efficiently finding patterns. For example, in LeetCode 49, group anagrams, you use hash maps to group strings based on a common characteristic. Similarly, in LeetCode 560, subarray sum equals k, prefix sums combined with hash maps are used to efficiently identify patterns within data. LeetCode 347, Top K Frequent Elements, demonstrates how hash maps and heaps can optimize solutions for frequency-based problems. Lastly, LeetCode 973, K Closest Points to Origin, focuses on efficiently processing large datasets with custom rules. Studying these problems can help you build a deeper understanding of patterns and techniques that are highly relevant to solving the invalid transactions problem. When considering alternative approaches, the brute force method involves comparing every transaction with every other transaction. While simple to implement, its O(n) squared complexity makes it unsuitable for large inputs where scalability is critical. A more efficient approach is to use a hash map to group transactions by name, which reduces the complexity to O(n). However, this method requires careful handling of edge cases to ensure correctness. Another option is a sorting-based approach, where you sort transactions by name and time, then perform a single pass to check for invalidity. This has a complexity of O(n) log n due to the sorting step, but it can simplify the logic for time-based checks. Key patterns to focus on in any solution include grouping data efficiently with hash maps, handling cross-references within datasets, and balancing simplicity with scalability to meet the problem's constraints and expectations. Thank you for following along. Today, we broke down an engaging problem, reviewed its constraints, and discussed an efficient approach to solve it. Remember, mastering such problems strengthens your data structures and algorithm skills, making you a more effective problem solver. If you enjoyed this session, don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!